Electromagnetism. It is everywhere around us. From the satellites that give internet to your phone, to the brain you might potentially have. But the study of electromagnetism had a very humble beginning.
What are you doing?
I've seen it in the movies, just... In 600 BC, ancient Greeks noticed that when you rub umber with a piece of wool cloth, it would attract leaves, pieces of papyrus, or pieces of strings. To understand why this happens, we have to fast forward to 1784, where Charles Augustin de Coulomb published what we now call the Coulomb's Law. Some famous inventors and their inventions are Alessandro Volta, who created the first battery ever, but it didn't look like this, it looked more like this. Thomas Edison, who holds the patent for the first ever commercially available incandescent lamp that looked like this. Nikola Tesla, who created the first AC system of generators, motors, and transmission lines. Alexander Graham Bell, one of the many inventors of the telephone. Seeing the past and its rapid evolution, it makes you wonder, what does the future hold for this field?
Okay, back to the present. We designed a simple experiment to demonstrate Maxwell's equation. For this experiment, all we needed was some copper wire, neodymium magnets, AAA battery, and a steel rod. The copper wire was coiled around the steel rod, and we produced a coil of copper, as you can see here. If we sandwich the AAA battery between the neodymium magnets and we place it into one end of the copper coil, it travels through the copper coil, as you can see here. But why does this happen? Maxwell's third equation states that the line integral of the electric field around a closed loop is equal to the negative of the rate of change of the magnetic flux through the area enclosed by the loop. Faraday came by this interaction with a simple experiment, as you can see here. With the switch open, no current flowed through the wire, and hence no magnetic flux was induced in the magnetic core. When he closed the switch, however, the ammeter spiked to one direction, say positive 10 volts, before returning back to zero. When the switch was opened again, however, the ammeter would spike in the opposite direction to negative 10 volts before returning to zero. From this, Faraday was able to derive Maxwell's equation in the form we know it today. In the case of this experiment, when the train is placed inside the coil, we complete a circuit and a current flows through the coil surrounding it. The coil is essentially multiple loops of current flowing in the same direction, which following Maxwell's third equation will give rise to a magnetic B field in the region of the train. This B field will exert a force on the magnets, propelling the train forwards.
You might be wondering what a homemade train has to do with futuristic technology. The answer is maglev. There are two methods currently used to levitate trains: electromagnetic suspension, which we won't be talking about today, and electrodynamic suspension, or EDS. To understand how EDS works, we will be talking about the Japanese superconducting maglev, or SCM. Analysis of EDS systems requires complex mathematical models because of the time and space varying magnetic forces. However, understanding the basic principles at work is not difficult. Imagine we have a wall of no-flux coils, and we move a magnet along the axis of the coils. The induced potentials cancel out due to the geometry. However, if we introduce an offset, current will be induced, and the induced magnetic field will produce a force that will return the magnet to the center or equilibrium position. A levitation is thus achieved. Guidance is achieved by connecting facing guideway coils underneath the track. Thus, when a maglev vehicle is displaced laterally, a current is induced in the loop and the magnets. The resulting induced magnetic field returns the vehicle to the equilibrium position. EDS systems can use magnetic forces for propulsion as well. To achieve this, the guideway coils are connected in a three-phase configuration and energized by a power substation. The shifting magnetic field produced by the guideway coils creates a force acting on the train and thus accelerating it. Thank you everyone for watching, and...
But wait! There's more! Even though Maglev is quite fascinating as an idea, there are also many other applications for electromagnetism in the future. One of them are plasma engines, which are rapidly developing ways of interplanetary space travel, and maybe they could even take us to galaxies far, far away. Furthermore, space travel could be assisted by railguns, which can also be used for planetary defense from asteroids. Thank you for watching, and we're gonna leave you with a bang. Bang!